Okay, so now I've made my life much easier. I was looking for an entire function. Now I'm looking only for two numbers, a and b. Right? Those are the only two things, the intercept and the slope. And so the first thing I'm going to need to do, so I'm going to start doing some probabilistic analysis. Okay? I want to know if you give me a distribution, a joint distribution of x and y, what do those a and b depend on, right? If you give me the distribution, presumably you're actually giving me everything I need to know. In particular, you're giving me the conditional expectation of y given x. So I want to know how it depends on those guys, on the distribution of the joint distribution of x and y. And we'll see that it actually depends on two very simple things, which are the covariance and the variance. Okay? That's it. Not 25th moment, not tails, nothing. Just like very simple summaries of this joint distribution. There will be also expectations, as you can see, that show up. So the first thing I need to assume is that the variance of x is positive, meaning the variance of x is not 0. Somebody tell me why I need to assume this. Well, yes, that's going to be a technical reason, but let's think about a conceptual reason. Yeah, so if my variance is equal to 0, then all the realizations of x are the same. In which case, my data looks like this. So this is the x, so that's some little x naught around, that's the expectation. And all my points are here. And good luck finding the best a line that goes to, well, I mean, actually it's probably easy to find a line that goes through those points. Okay, so I can talk about the theoretical regression line, and the theoretical regression line is the one that will just be the closest in expected squared deviation. Okay, so this is, let's parse a little bit what's happening. Okay, so I have y is equal to x, and I'm going to assume that the conditional expectation of y given x is this guy. Okay, a star plus b star x. And I claim that a star and b star x are actually precisely the guys that minimize the distance from y to a plus bx. Okay, in squared expectation. So you can see here that this is not something I can do as a statistician, because this depends on this expectation right here, right? And right here, sorry. And this expectation right here depends on the joint distribution of x and y, right? I mean, if you look at what's behind there, there's y and there's x. So this expectation is really an integral with respect to the joint density of x and y, which I do not know. So this is not something I can do. This is why this is a probabilistic analysis. I'm trying to understand, if my truth looks like something, what is my data going to look like? That's what I'm trying to do at this point. Okay, I'm only on the truth side. Okay, so how do I do this? Well, let's just try to minimize this function. So this function actually turns out is convex. Okay, it's a quadratic function, so it's something that looks like this. And so all I have to do is to set the derivatives equal to 0. Okay, so derivatives and expectations can be interchanged under some technical conditions, which will always be satisfied in this class. And so what I want to do is to look at the partial derivative with respect to a of expectation of y minus a minus bx squared. Okay, so if I look at the derivative here, what I'm going to get is 2 times. So minus 2 times expectation of y minus a minus bx. And I want to set this equal to 0. Okay? Everybody agrees with this? Okay, so now I have something which is linear, so I can pull my expectation all the way. So this is going to give me, so of course this guy goes away, that's equal to 0. So this gives me e of y minus a minus b e of x is equal to 0. Okay, and this is actually where I get my a in the second line. This is telling me that a is equal to e of x, e of y minus b e of x. And of course, I need to put some stars once I set it to 0. Okay, so that tells me that a star is an implicit function, depends on b star. So I need to find my b star. So of course, to do that, I need to take my derivative with respect to b. Okay, of the same thing. Okay, so I get, and so I get minus 2. This time I have an x that's going to come out, right? So it has to stay inside the expectation. And then I have the same thing, y minus a minus bx. And as before, I want to set this equal to 0. Okay, so when I set it equal to 0, this is giving me my solutions, a star and b star. So now let me solve this. What I'm left with, so this minus 2 goes away. And so it says that expectation of xy minus a star expectation of x minus b star expectation of x squared is equal to 0. So, okay, so now I have to solve for those two guys. So I'm just going to plug in my a star equal to this expectation. Okay, so that tells me the expectation of xy is equal to minus expectation of x, expectation of y. So I'm just replacing here by expectation of y. And then I have plus b star expectation of x. And there's two of them, one that's coming from this guy and one that's coming from that guy, minus b star expectation of x squared equals 0. Now you can start seeing that there's things that we're actually used to. What is this? That's the covariance between x and y. And this guy here, expectation of x squared minus expectation of x, the whole thing squared, is the variance. So this whole thing here is minus b star variance of x. And so now I solve for b star, and it tells me that b star is equal to covariance of xy divided by variance of x. Okay? And then, of course, a star is just expectation of x minus b star expectation of y. And I can just plug in the value that I got from my b star, but I cannot really go any much further. All right, so this is just covariance of xy divided by variance of x. So rather than just like leaving you with this computation, which hopefully is correct, let's just look at it a little closer. And what we can see is that this b star, what is this b star? This b star is the slope. Okay, it's the slope of my curve. And what is the nature of this b star? It's a covariance here. So it's really measuring how much x and y tend to move in the same direction. So if the covariance is positive, you're going to have a positive slope. If the covariance is negative, you're going to have a negative slope. And this variance term here in the denominator is really here to just adjust from the scale of x, right? Because this is a slope. And so the slope is telling you by how much you increase y, the expectation of y given x when you increase x by 1. And so if you start changing x and turn it from Celsius to Fahrenheit, your slope will be affected. And it's just taken into account by this variance right here. Okay, well, there's a variance term that shows up right here. But if you can see, this is homogeneous in x. If I multiply x by 2, my covariance will be multiplied by 2, but my variance will be multiplied by 4. Okay, so that's what it's taking care of. Okay, so it's not super transparent, but there's nothing mysterious about the final form of b star. A star, well, a star is just the intercept. That's what it is. That's where this line crosses 0. That's what it is. Okay, I'm not going to interpret that one. Well, it's 0 if x and y have mean 0 at least. Okay.